Testing 1, 2, 3. See if I can hear me. All right, so I've unmuted my microphone, so if people want to give me a thumbs up on the chat line and let me know if you can hear me okay. Okay, so you can hear me. Good. Um, so as much as this picture is beautiful here, it doesn't show you a whole lot of math. So I have two monitors and I'm working on two of them. So if people have problems, they can walk in and out. You guys, you can use the Excel sheet. Sorry, me and Judy can't hear you somehow. Hello? Um, all right, so whoever's on the chat, could everyone say flowers? Type flowers if you can hear me. So everybody on the chat who's listening in, type flowers if you can hear me. Ah, never mind, Johan, you, everything's good. It's that Bluetooth, I'm sure, right? There you go. Flowers, flowers, good, flowers. Everyone's typing flowers. All right. So, who should I scare first? That's the question. Let's see if I can find something scary. I can hear now. Okay, Judy can hear now too. That's good. I'm waiting for Paulina to join and write 400 messages really quickly, interrupting herself. So let's see if that happens. Good. And Judy can hear as well. Calculus. All right. Anybody have any questions so far from the from what you guys are reviewing? Quick question: will functions be on the test? What do we do with functions? Well, we did do functions. Yeah, we had well, a quadratic is a function, right? So we did quadratics, and of course we did transformations. So a function is anything that you can graph that passes the vertical line test. So in general, you have to be more specific about functions. I mean, the unit is functions that we were starting on, right? Or that we're in the middle of. Oh, Jeffrey in your Vertex, no problem. You want to show how to find the vertex. So the grade 12, the grade 12's tuning in. This is why we complete the square, right? So we have a function. I'll do one like with a number, something ugly like this, Jeffrey. So there's other ones, of course, I could give you one like this, which is much easier to do when there's the number in front of the x squared is 1. So let's do both of them just so you can see the difference between the two of them. I'll move this down here so you can see. I believe my window, you should be able to see everything in my window according to my thing. It looks okay from my end. So let's do the easy one first. Vertex, so you have to complete the square. So to complete the square, we should take your bx, the b in this middle here, and we need to divide that by 2. and square this, okay? So if you divide 4 divided by 2 and square it, you get 4, okay? I put my 6 over here, but of course if I add 4, I have to subtract 4 as well. And this here creates your perfect square. So if you factor this, you should get x plus 2. So there's your perfect square. So the whole point of dividing by 2 and squaring this number here is to create this perfect square. But as soon as I introduce a 4, I have to subtract the 4 because in functions you can't just add a 4 in randomly, right? You have to balance the... okay, there you go. Sorry. So as soon as I add the 4 in here, I have to subtract the 4. Now, negative 4 plus 6 is positive 2, right? And then from here, you can read your vertex. Okay, so your vertex, the 2 is always the same, and the x for your vertex is always the opposite sign of this, so it's negative 2. So there's completing the square when you have a 1 in front. So that's your vertex. All right, if we go up above to check the vertex here, one extra step you need to do is take out the 2 out of this front here, like so. Oh, sorry, I have to divide out the 2 here. So divide out a 2 everywhere. And this is where it gets a little bit ugly because it's 7 over 2, right? And now you follow the same steps here. So in order to do this, you divide 2 by 2 and square it. So if you do that, you end up getting a 1. But if you add a 1 into this bracket, you also have to subtract 1 to keep the balance, because once again, you cannot just add numbers into this function. And then we have 7 over 2, like so. And now this becomes our perfect square. So we have x plus 1 all squared, and then negative 1 plus 7 over 2. What's this? 3.5. So we have 2.5, which is 5 over 2. Like so. And remember, this 2 is on the outside of this bracket here, right? So you can even put big square brackets just to make sure you don't mix that up. All right. And then the last thing you need to do is bring the 2 in, multiply it there, bring the 2 in, multiply it there, like so. And you end up having 2 times x plus 1 squared plus, well, 2 times 5 over 2, it's 10 over 2. 10 divided by 2 is 5, and we have that. And now if we look at the vertex, we have 5 here, and in this case, it's also negative 1 here. So those are 2 examples of putting it into the vertex and reading the vertex, right? And knowing the vertex form. So remember your vertex form, the general form of that is a times x minus h. Whoop. Yeah, sure. A times x minus h squared. I'm really lagging here, sorry. Plus k. So there you go, that's your vertex form here. All right, no worries. Anybody got anything else that's freaking them out before their exam? Alexander, you must have something. I know you. Venn diagrams, right? Could you give us an example of explaining the do not cancel zero? That's a common factor from both. Sure. You don't like this one, I know, Isadora, but You have to get it through your head. Hold on a second. All right. So, I mean, the easiest idea you can think of is this. Watch, if you had x times y times z is equal to 0, all right? If you had something like this and you divided everything by x, y, and z, right? Or let's imagine, let's take something simpler. Imagine you had x times y times z and you divided out y and z, like so. Your only solution would be x is equal to 0. So if you think about it this way, this doesn't make any sense because in this expression or in this equation, you have two other solutions, right? Y could be equal to 0 and z could be equal to 0. So these are three solutions of this same idea, right? So if I give you anything in general, if you can equate something to 0, all right? So let's make it a square times a triangle times, I don't know, a diamond, right? If you divide any of these shapes out, and of course inside these shapes could be other things like, I don't know, in here it could be x minus 3, in here it could be x plus 2, and here it could be just x. So the idea is that if I divide out x everywhere, right, meaning if I divide out this diamond with the x in the middle, x, you've eliminated the shape. So once you have these blocks of algebraic expressions, I guess you would call them, right, multiplying each other equals 0, you cannot just divide out something like this, okay? The only thing that confuses you is sometimes they'll have, say, instead of equating to 0, they'll have this square times triangle times diamond equals something like a square times a diamond on this side, and then you'll say, well, it's not equal to 0, so can I cancel out divide by a square and divide by a diamond? No. What you can do is you can throw this over onto this side here, right? And you have something like this minus, right? And from there, you have a common factor. So this occurs a lot in math, where you now take out a common square, you take out a common diamond, and what you're left with is this triangle in here on one side minus, well, there's nothing left here, so there's a 1. Okay, so from the very beginning, if we divided out this triangle and this square, they would be gone, and all we would have left is this diamond and the square. We would just have a triangle is equal to 0. But as you can see, look, one of my solutions is triangle actually minus 1 is equal to 0. So here is one solution, right? And our other solution is these two multiplied against this could equal 0. So our square could be 0. So 0 times this is 0, of course. And finally our diamond here, that also could be 0 because you have 0 times that is also 0. So if you start dividing stuff out right from this beginning point, you can see, look at all the solutions you have. One solution, two solutions, three solutions. It's just something that you cannot do. So the classic example is this one here, right? Divide out by x, divide out by x. You have x is equal to 1, and that's the end of your solution. But of course, if you look at these two, if you put 0 here and 0 here, well, they are equal, aren't they? So x is equal to 0 as well. So this is the solution that you eliminated because you divided that out. And it goes for cosines, sines, anything else like this, right? Anything that can produce a solution, you have to make sure you can't divide it out of the equation. I don't know if that helps you at all, Isadora, or not. I mean, I can use a sine and a cosine. I can use a, what else? Sometimes logs, but you guys didn't learn about logs, so I'm not going to start on that. Right? Oh, sorry. All right, no worries. Let's see. I'm reading yours. Alexander. Could you explain some main concepts of mutually exclusive events, tree diagram, conditional probability? Okay. So I'm going to delete this here for now. I'm going to delete this here for now. I'll pull in another one, and I'll make sure that it's in the frame so that everyone can see it. Okay, so I mean, you were introduced to some formulas. We had P of A or B is equal to P of A plus P of B minus P of A and B. And the main idea is that if you have mutual exclusion, right, here, then there's no shared piece in these two circles. They're completely separated. So your A and B in this case, that's 0. So if you're reading some sort of word problem or anything that has to do with mutually exclusive, in this formula, this piece here would be 0. Now, if you have independent events, right, independent events, then that would mean that this piece here, P of A and B, well, that's equal to P of A times by P of B. And an independent event, when do we multiply probabilities? Well, if I were to create a tree diagram like so, like this and this, mutually exclusive events and independent event appears on both of them. So I don't know, let's make up something. So let's say that's 1/2, 1/5, 4/5. Here's 1/2. Let's say this is 1/3 and this is 2/3. Okay. So we did tree diagrams, and we know going this way, we multiply down the diagram's arms to get the final probabilities at the end of my tree diagrams, right? So since you have this times this, these are what we call independent events. So for example, this could be something like you taking your car, and then this could be something like how many times you're late. You have a 2/3 chance of being late. So up here, you could be taking the bus, and once again, you have a chance of being late or not late again to the office. But they're completely independent. Your car and being late is independent. One day you could have lots of traffic, one day you could have no traffic. You have no idea. So of course, it's the probability of taking your car times the probability of you being late, which kind of looks like this, doesn't it? A is event A here, this is event A, and this is event B. All right? And you're ANDing them. So think about it in a sentence. I'm taking the car and I'm late, right? Opposed to, I'm taking a car and I'm late, or I'm taking the bus and I'm late. So you can talk through this tree diagram to figure out what these are, okay? So that's how you have independent and mutually exclusive events is something like this. Ask yourself, can you take the bus and be late at the exact same time as taking a car and be late? That's impossible, right? You're not going to cut yourself in two and put yourself in two different vehicles. It's just impossible. So this is what happens when you have independent versus mutually exclusive events. So they both exist on a tree diagram, right? Okay. So there's some main concepts of mutually exclusive events in tree diagram. And then conditional probability, I told you that this is this thing A given B, right? And you have to find the probability of A and B over the probability of B. And I told you that this line, when I hear the word given, it's conditional probability. Now, given doesn't always necessarily mean that. It could be at or you could have something like Alexander takes the bus to school. What is the probability that he's late? So what I've done is I've made a blanket statement that says, given that Alexander takes the bus to school, I don't have to use the word given, so be careful because they don't have to use this word given. It's just they use it a lot because it shows the idea of conditional probability. All right. So, anybody else have something? The formula written at the top is only for mutually exclusive events, or is it the generic one? Which this one here, this one's called, this is for combined events like this. So combined events can be mutually exclusive or they can be independent. And usually in the question, it says something like if they are, if they're not. I sent you guys the formula booklet, so you should have it. Look on your formula booklet. So that's probability there. In general, the tree diagrams are quite easy. It's when you guys have to start doing conditional probability that you get mixed up. So anyone else have some issues with their math? We can also talk about geography, but I have a feeling that it would be useless. In which cases do you substructure one while doing the conditional? I'm not quite sure what you mean, Alexander. In which cases do you substructure one? Subtract. So in which cases do you subtract one while doing conditional probability? In what sense? Like, I mean, I can give you a conditional probability example from this tree diagram, right? I could say, what's the probability that you take the car given that you're late, right? Something like this. So it's the probability of taking your car given that you're late. And I mean, most of you guys, I think, got this on the re-quiz. So it's car and late over just late. I mean, the only time I think about subtraction is like if I do the complement of something. So if you have a 20% chance of taking the bus, you have 1 minus 20% chance of not taking the bus. So where do you take the car and you're late? Well, you take the car and you're late down here. And then what's the probability of you being late? Well, that occurs here and it occurs here. So you have to add those ones together. And of course, I can give you anything with conditional. I can give you a Venn diagram, probability, sample space, anything I want, right? You just have to know how to use this formula. I could give you a Venn diagram. I could give you 2 circles, or I could give you 3 circles, right? You guys should be able to do both of them, I believe. Are there any common phrases which identify mutually exclusive events in the word problem? I like given that refers to the conditional. No, usually what it'll say is it'll be something like the following. I could say prove that it is mutually exclusive, prove that it isn't mutually exclusive. There's a bunch of different ideas, but they're usually not in word problems that we have that, right? So I don't think you have to worry so much. So I think there's probability in this book. So if you guys want to take a screenshot, I can give you a Venn diagram to try. Sets and Venn diagrams. Problem solving with Venn diagrams. You want something crazy? Well, look at this one. I shouldn't be showing you guys this. I should put this on your test. This one looks really good. But if you want to take a screenshot of something to do, how do you find vectors from quadratics? In what sense? Like, we talked about vectors being a transformation, right, Aaliyah? So, for example, if I had something like, normally they'll say something like you have some parent function or any function. It doesn't matter what happens, right? And it's transformed by the vector 3 minus 2, something like this, right? So what happens is essentially it's saying that the x, it's going up 3 to the right and your y is going down by -2, all right? So if this case, whatever your function is, what you should do is if it's going to the right, then this x becomes x minus 3, right? Because that makes a shift to the right. And then if we subtract 2, that shifts down. If they say something like the following function originally looked like, I don't know, Control Z, here I'll give you one. Following function started off looking like this, x, let's see if I can do x minus 4 squared plus 2, and a new transformation was applied, and it now looks like this, x plus 3 squared minus 2. Provide the transformation vector for this, right? So what has happened is you're at 4 and it's moved 7. Now, which way did it move? It's moved to the left because x minus 4 would have been some function where it was off to the right if we were to graph that. And this is, remember, this is in the vertex form here, right? X minus 4 squared plus 2. So we know that the vertex is at 4, 2. So if that's the case, here's this point, random point 4 comma 2. Now it's at x plus 3 squared minus 2. So if I have this new point here, it's been moved over 7 that way, hasn't it? Right? So now it's at minus 3, minus 2 down here. So the vector that was applied to this transformation was minus 7 because it moved x backwards negative 7. And it moved it down 2, so the transformation is down 2. So if you were given this one here, and then they say this happened after some transformation of some vector, you would have to describe the vector. Maybe they say, please give the values of a and b based upon the vector like this. And you get negative 7, negative 2, something like this. All right? Does that answer your question, Aaliyah? No worries, no worries. Alexander, I'm just looking at your thing. Could you make one example question for providing the events are mutually exclusive? I don't think I fully understand. All right. Watch. Imagine I give you a, I don't know, let's say I give you a Venn diagram. I go like this. I go like this. I'll make up some probabilities. Hopefully this will work. I'll say the probability of A is 0.1. The probability of B is 0.2. The probability of A or B is equal to 0.7. Is this a mutually exclusive event or not? Right? Something like this. So if I ask this, that your probability of A times probability of B would have to be equal to 0. But right away, if I multiply these two together, that's impossible. 0.2 times 0.1 is, so this does not equal 0, so this is not a mutually exclusive event. Okay. You just have to fool around with these numbers, Alexander, and then figure out A and B. Maybe they tell you in the question that the probability of, maybe they try and tell you to find the probability of A and B. And when you find it, it's 0.3, and then so 0.3 does not equal to 0, so there you go, they're not mutually exclusive. Okay. Some examples, AK on logarithms. So we can go anywhere. Specifically, if you want to do some natural logarithm examples, the best thing to do is just make sure you understand the book ones, because the book is really good at just checking. So if I go to the logarithms chapter here, and I'll show you some. So logarithms are here, and the natural logarithm is here, 6D. So solving for x, they start with simple logarithms, okay? So I can do a few of these if you want, just to make sure you understand that. So I'll start off and I can do these two, and then we can go down here. You can the ln or natural logarithm is the same thing as any other log. So you should know your log rules when you're adding two natural logarithms or subtracting two logarithms. I'll grab some just in case you want me to do, but if you understand that, just like tell me on the chat and I won't bother doing them. So that. Next, there's these type here, show that. So these are log rules as well. So if you want, I'll put a couple on there and you can tell me what you want to look at. So that's the next chunk. So I'll call this number 1, number 2, and number 3. So have a look at these 3 and tell me which ones you want to do as reference, and I'll find some more separate ideas on logarithms if you want. Hold on. So if there's any of those that you want me to do, and then after that, you just have to manipulate log equations. And remember, log is the same thing as ln, except ln is base e, right? So you should be able to solve for anything here. And then all you need to do is switch log in with ln, and then you can do the same thing. It's the same rules, except these log, it's base 3, and yeah, so question E. 1E, or I have 6E, and I have 3E here. So which one do you want? All right, 3E, okay. So in order to do 3E, you have to be very good at your surds and algebra, because you have this 1 over square root 2, which is quite ugly. So let's take a look at it. And I introduced 2 ways in order to solve logarithms in general. You have 2 options when you're solving logarithms. It's either you try and make a log of some argument equal to the log of some other argument, like so. And as soon as you do that, you can throw away the logs and solve for a is equal to b. All right, so if you want to do it in this form, we can try that. So if you notice, I have ln of something, let's call that a. Sorry, in this example, they want you to prove that this looks like this. That's what they want you to do. I'm sorry, we're not solving any logs. We're just manipulating it so it looks like in another form. So I want to show that this side looks like this side here. All right, so the first thing I do is go 1 over 2 to the power of 1/2. I change my square root to the power of 1/2. The next thing I do is I bring this up using my indice rules, and when you bring it up, it becomes 2 to the power of -1/2, like so. And then finally, there's a log rule that says if you have an exponent in the argument of your log, you can bring it out front here like that. And now it's gone. And we finally made it look exactly like they wanted us to do. All right. So be careful. This algebra is just manipulating square roots and manipulating indices. This is the hardest part. Anything else in there with logs that you see on this page that you want me to work on? No worries. Anyone else have something that they want me to try? So you want to know the topics for 13? It's on the Excel sheet. If you don't have an Excel sheet, you have to tell me who your name is other than what the fudge is going on. The Excel sheet, I've highlighted everything. So if we find it here, this is the easiest way now that we're going to find the, yeah. So if you go to OneDrive, where did I have it? Math, paste by document. All right. No, that's not what I wanted. These ones are, no, that's not what I wanted either. Where is it? 5A for the exam practice. Yeah, hold on a second. So you want me to go on Shobi, I guess, Jeffrey? All right, you have the Excel, good. So 13, 5A exam practice, okay. You mean the one that I sent out the other day? Is that what you mean, Jeffrey? Like the mock exam that I sent to you guys on email? Someone who's going to talk to Paulina tonight has to tell her that, yeah, the calculator's on my desk here. I'll leave it in the corner just because I got an email from her. Sample mock exam. Yeah, Isadora, experimental is like you're flipping a coin and you see what happens. Theoretically, you should get a 50-50 chance. But there is, if you have an experiment and you flip a coin 10 times, there is a probability that you can get heads 10 times in a row. The probability is very low, but it's possible. So what you experiment versus theoretically could be different. That's basically the difference between the two. Is this the one that you want me to do, Jeffrey? Can you see it? Give me a thumbs up if this is it. All right. Great. Grade 12s, you can look at this because we're going to do this year as well, so that next year you don't even have to think about it. Sequences in series. So figure n contains 801 line segments. Show that n is equal to 200. So if you keep on making this sequence, it's going to be more and more. So the first sequence here has how many lines? 4, 5, right? The second sequence has how many? 5, 6, 7, 8, 9. The third sequence has 9, 10, 11, 12, 13, and so dot, dot, dot. And you can see that the common difference is 4. All right. So this is an arithmetic sequence because it's going up by 4 every time. So this pattern is going to keep going up by 4. So this is the case. We can use It says figure N contains 801 line segments. So we have way down here is N. So this is like U1, U2, U3, and this down here is UN. So we know that UN is equal to 801. And we also know that UN is equal to U1 plus N minus 1 times D. So now we look at this and ask ourselves, do we have everything else to solve for N? So we're solving for N. So that means we should find D and U1 so that we can isolate for N. And luckily we do have U1. It is 5. N we don't have, and our common difference in this case is 4. Rainbow that over. 801 minus 5 is 796. N minus 1 times 4. I would divide by 4 on each side. So we have N minus 1 is equal to 1, 9, and 6, is it? 196, if I'm right. And then you rainbow that over there. So N is equal to 197. Let me just do this on paper again quickly so I make sure. 1, 3, 49. No, I screwed up. No, it's 49. Oh, sorry, 4. That's 3. And 9 times 4, 36. 3. Bring down the 6. And then 9. Oh, 199. So this should be 199, sorry. And then I throw this over here, so that actually becomes 200. So check the mark scheme and see if that is okay. Good, all good. So there's that one. I deleted that, so where the 1 comes from in the second vertex. It's 2x squared plus 4x plus 7, right? So this is a 7, right? So I did this, and then the 1. So in order to complete the square, you take this number here, divided it by 2, and square it. That's how I got my 1, Jeffrey. That's the method in order to complete any square. If you have something like this, the theory is this: if you have a plus b squared, you always are going to get a squared plus 2 times the first term times the second term plus b squared. Okay. So if this is the case, what the complete the square does is that you need this piece here squared so that you can have a perfect square. That's essentially what they're saying, is once you have this, you have a plus b. So what I'm doing is I'm taking this here and I'm dividing it by 2 and I'm squaring it so that I have this b squared, so I end up getting a perfect square. So an example here, if I divide by 2 and square it, in those brackets, I would have x squared plus 2x plus 1, right? And so this creates this b. It's like 1 squared. So whenever you have the first term squared, the second term squared, and 2 times the first term, the second term, then you get this perfect squared form right here. That's the perfect squared form. Question from discriminant paper practice. Yeah. Was there anything in here that I gave you with discriminants? Let's see. Did I skip a discriminant? Was there any discriminant in here that I gave you guys at all? It's probably easy if I just grab something from the book, because the book has very similar examples that are on the past papers. So if we go to the book and try a discriminant problem, let's see, that's in functions, specifically discriminant. Where did we do our discriminant again? Quadratic functions, using the discriminant. So in a specific question, we could do anything in any one of these problems here. So if you want to do a discriminant problem, here is an example of one. So there's A, B, and C. So the discriminant is b squared minus 4ac, and it's either greater than 0, less than 0, or equal to 0. And in this problem, they actually check all three of them. So cuts the axis twice, so this is I, touches the axis, which is I, and then misses the axis, which is I. So those are the three here. So you can check all three of them depending on what you want to do. So for instance, if it cuts the axis twice, our value for A, so if we do A, our A is equal to 1, our B is equal to 3, and our C is equal to K, like so. So B squared minus 4 times A, times our A, which is 1, times C, which is K, and that should be greater than 0. So if we do that, we have 9 minus 4K is greater than 0. I put the 4K on the other side. I have that divided by 4 divided by 4, and I have K is less than 9 over 4. So there is a simple discriminant problem. All right, and as you can see, if you have it less than 0, this would be the opposite sign, and of course if it's equal to 0, this would be equal in this case, right? So you can look at all these different variations. So depending on what your K is, if you put a number here, remember K in transformations is a shift, right? So if you add a number, it goes up, down, wherever it goes, okay? So there's a very generic, simple, so you're looking for a question that says 2 repeated roots, which means touches the x-axis, that's repeated roots. Misses the axes is non-real roots. And then two distinct roots are cutting the axes twice. So this is for grade 13, yes. We did discriminants. A, B, C. So this one here is probably going to be much crazier. Yeah, oh. Lots of people missed classes before Christmas. Lots of people missed classes after Christmas. And so I lost track. And when people didn't check with me or ask me, it's possible that they completely missed. Like the discriminants didn't take much time to look at. It's basically the idea is you have a quadratic that crosses twice, quadratic that crosses none, or a quadratic that just touches the line. And this is the whole idea behind discriminants. So, and the discriminant formula is on the formula sheet. It is b squared minus 4 times a times c. So I'm going to probably continue on working on my exams if anybody doesn't have any last minute questions. Okay, I have a question. I don't know which questions to ask. Yeah, I mean, the term is going by slow, and as soon as we get off this exam, it'll tell people what they need to do and what they don't need to do for the term. We had a discussion about people missing a lot of classes, and in the IB, if you miss classes, then you're in trouble. In the IB, if you don't do any work, you're also in trouble. So something that we have to look at, whoever this is, I don't know, 4A of the exam. So whoever WTF is, sorry, I don't know your name. You can keep your name in disguise, but maybe I'll know from looking at your exam afterwards, right? Or not if there's more than one person. 4A of the exam, so this one here. So for this question here, find the common ratio. I told you guys if you want to find the common ratio in a geometric sequence, it's very simple. you just go next divided by previous, right? So the first two terms, so if you want to know your common ratio, that is the next. So if this is u1 and this is u2, it means it's log 2x divided by 2 log 2x. And if you do that, what's going to happen is these logs actually cancel, and you have a 1 there, so your common ratio is 1/2. The topics in trimester 1 are going to be, yeah, I can ask you to do triangles tomorrow. We talked about this. Remember, the teacher came in and I said, what are we going to be examined on? And he said, oh, I examined straight from the beginning, so you have to know your cosine rule, sine rule, stuff like this, quadratics, everything. For the next piece, Jeffrey, it's just this, the sum of an infinite sequence is this formula. So I just plug in u1 and r. And 1 minus 1/2, this becomes 1/2. 2 divided by 1/2 is 4, and then you get 4 log 2x. And then for C, same idea, but it's an arithmetic sequence. So if you want to find your common D, it's as simple as going next minus previous, right? Giving all you guys these formulas. D is equal to next minus previous. So I have u1, u2, u3. The next is, let's find 2 in a row, log 2x over 2 minus previous, which is log 2x. Find D given your answer is in an integer. When you subtract two logs, you actually multiply their arguments, or sorry, you divide their arguments. So let me do this again. So if I want to combine these two together, I would go x over 2 divided by x. That's how I would create this mega log, right? And x over 2 divided by x is like x over 2 times 1 over x. So the x's would actually cancel, and you would get log base 2 of 1/2. And then from there, I would put my 2 above here using indices laws. So you have log 2 to the minus 1. I'd bring my minus 1 out front here, like so. And then you'd have log 2 of 2, and that's equal to 1, so you end up getting negative 1. And then the rest of 4. So it's the sum of the first 12 terms. So S12 is equal to n over 2 u1 plus n minus 1 times d. Now you just have to insert everything in. So 12 over 2 times our log. First u1 is log 2x. N plus n minus 1. So n is 12 minus 1 times the common difference we figured out was how much again? -1. So 6 times 12 minus 1 is 11 times that is -1. So 2 log 2x minus 11. And then I bring this in, you get 12 log 2x minus 66. So all you have to do is, it's just formulas, this whole question, right? And knowing U1, U2, U3. And then, let's see, as you go further, you have the next bit of the question. Given that S12 is equal to half the sum of the infinite sequence, so what I would do is I'd write something out. So S12 should equal to 1/2 of S infinity. That's what they're telling you. Find x given your answer. So at this point you should go 12 log 2x minus 66 is equal to half of sum of the infinity. So I have to go back and find the sum of the infinite, which is 4 log 2x. So this question requires you to be like amazing in logs and just understand logs. And so I told you guys you have to either make one log of something equal to another log, or a log of something equal to a number, so you can do BOA. So what I'm going to do is 1/2 times 4. I'm going to make this easier. So this is 2 log 2x minus 66 and 12 log 2x. And then I'm going to divide everything by 2. So this 2 goes away. This becomes 33. And this becomes 6. And then what I'm going to do, what's the easiest thing to do? I guess I could put this log on this side so that I have a log on one side, and I'm going to put my 33 on the other side, so I have the number on the other side. So we have 6 log 2x minus log 2x is equal to positive 33. 6 log 2x minus 2 log x, these are like terms, so this can be written as 5 log 2x. I'm going to move my screen a bit, hold on. All right, and that's equal to 33. Now I have to solve for x. Remember what they ask, they say find x, so you have to solve for x. That's, you have to have a goal with your logs. So I have to somehow rip out this x. 66 came from back here. I had a 6 there from the 12 divided by 2. And then when I FOILed it in, I had 6 times 2 and 6 times -11, -66. So once I've done all this stuff, you've created this equation, I've done all this stuff, I actually have to get this x on its own, so I divide by 5 on each side, divide by 5, and finally I have this thing which is log 2x is equal to 33 over 5. Now I use BOA, base to the power of other side equals argument. And now if you look at the question, it says give your answer in the form 2 to the power of p, where p is a rational number. 2 to the power of a number, and 33 over 5 is definitely a rational number. So your answer for your P is equal to 33 over 5. So there you go, Jeffrey. No worries. That's an intense question. You guys have to be awesome at your logs. You have to always know what your goal is for a log. Putting it in one of these two forms. This form, log is equal to a log with your arguments, or log is equal to a number, and then you can do what I did down here. If you can't do that with your log equations, that's your ultimate goal for log equations. If you can't do those, then you can't solve logs. So all right, I'm almost done here. It's getting late and I have to still do some stuff for your exams. So you guys will just have to suffer through the night or go to bed early, and hopefully it'll be okay in the morning. So no worries. Then it just means that you know everything and you're going to get 100% on my exam. That's all that means, right? So no problem. You guys have a good night. I hope you sleep well, and I'll see you in the morning. If someone sees Paulina, tell her calculator's on my desk.